I'm going to start off by looking at the near-term temperature record and then go back successively further in time, looking at the range of temperatures in historic and then geologic record. Then we will examine the role of the sun in changing climate, and following that, the contribution of anthropogenic warming from carbon dioxide. I will finish up by combining the solar-driven prediction with the anthropogenic contribution to make a prediction of climate to 2030. The satellite record is the highest quality temperature data series in the climate record. We have 28 years of satellite temperature data. It shows that the temperature of the southern hemisphere, which is the lower line, has been flat with a slight increase in the northern hemisphere. Note the El Nino peak in 1998, which is this thing. If it doesn't feel hotter than it was in 1980, it is because it isn't hotter than what it was in 1980. Most rural temperature records in the United States were set in the 1930s and 1940s. Greenland had its highest recorded temperatures in the 1930s and has been cooler since. That is why it is possible to select a number of rural US temperature records and come up with a reconstruction that shows that it's cooler now than what it was 70 years ago. And in this case, appreciably cooler than what it was 70 years ago. The 1.5 degree temperature decline from the late 1950s to the mid-70s was due to a weak solar cycle 20 after a strong solar cycle 19. After the invention of thermometers, records started to be kept. This is one of the longest temperature series and is actually an amalgamation of a number of sites. The recent record has been contaminated by the urban heat island effect. A number of interesting things can be seen in this record, including the depths of the Little Ice Age in the late 17th century, when the Thames regularly froze over, and the Dalton minimum, which was the last time the Thames froze over in the City of London. The warm period of the 1930s and 1940s, seen in the shorter US rural data set, is also evident, and the rise to the El Nino in 1998. What is also interesting is the 2.2 degree temperature rise from 7.8 degrees in 1696 to 10 degrees centigrade in 1732. This is 2.2 degrees in 36 years. By comparison, the world has seen a 0.6 degree rise over the 100 years of the 20th century. That temperature rise in the early 18th century was 4 times as large and 3 times as fast as the rise in the 20th century. The significance of this is that the world can experience very rapid temperature swings, all due to natural causes. The temperature peak of 10 degrees wasn't reached again until 1947. To reconstruct climate prior to thermometer records, isotope ratios and tree ring widths are used. This graph shows the medieval warm period and the Little Ice Age. The peak of the medieval warm period was 2 degrees warmer than today, and the Little Ice Age 2 degrees colder at its worst. The total range is 4 degrees centigrade. The warming of the 20th century was 0.6 degrees by comparison. This recent warming has melted ice on some of the high passes in the Swiss Alps, uncovering artefacts from the medieval warm period and the prior Roman warm period. The previous graph is derived from this graph produced in the 1990 report of the Intergovernmental Panel on Climate Change. The medieval warm period has become inconvenient to the IPCC, so they haven't mentioned it since. It was warmer again not long after the last ice age ended. Sea level was 2 metres higher than it is today. Since the Holocene optimum, we have been in long-term temperature decline of about 1/4 degree per 1,000 years. the last 3 million years have seen extreme fluctuations in temperatures at mid to high latitudes. This graph shows the last 400,000 years of data. The temperature range from top to bottom is 10 degrees centigrade. Note that the carbon dioxide levels lag temperature by about 800 years. Also interesting is the amount of dust, with the dust correlating with coldness. Colder is drier and warmer is wetter, generally. Large areas of Australia are covered by sand dunes that formed in these ice ages and are now stabilised by vegetation. We are currently in an interglacial that has lasted 10,000 years to date. You can see from this graph that interglacials are usually much shorter than that. So the next ice age is overdue. Ice ages started about 3 million years ago, initially with a 41,000 year cycle and then with a 100,000 year cycle. For the most of the last 600 million years, the Earth's climate has been steady at an average temperature of 22 degrees, apart from periods of ice ages. Ice ages have occurred roughly 140 million years apart, driven by the Sun's position in the spiral arms of the Milky Way galaxy. What this record shows is that there is no correlation in the geological record between atmospheric carbon dioxide and global temperature. The Earth went into an ice age 450 million years ago, despite a level of atmospheric carbon dioxide that is 10 times higher than what it is today. 150 million years ago, atmospheric carbon dioxide levels were 5 times what they are today, but that didn't stop a Cretaceous-aged glaciation. Later in this presentation, we will see why that carbon dioxide would not be expected to have any influence on global temperature over geologic time. Before we leave this graph, I should mention that the proponents of anthropogenic global warming state that high atmospheric carbon dioxide levels will cause the oceans to become more acidic, which will kill off coral reefs and other types of marine life. Coral reefs formed back in the Devonian period when atmospheric carbon dioxide levels were 10 times what they are today. The energy that stops the Earth from looking like Pluto comes from the Sun, and the level of this energy does change. This graph is of sunspot cycles since 1700. The average length of a sunspot cycle is 10.7 years. The Dalton minimum is a period of lower temperatures from 1796 to 1820, caused by the low amplitude of solar cycles 4 and 5. We are currently near the end of solar cycle 23, is this one. When solar cycle 23 ends is very important, as we'll see in the next few graphs. This graph shows the temperature response to solar cycles 5 and 6 at 3 European stations. There was a 2-degree decline at Oberlach in Germany over that period. Next slide, please. That's it. There is a better correlation between temperature and solar cycle length rather than with solar cycle amplitude. I produced this graph using data from De Bilt in the Netherlands. The slope of the line is 0.6 degrees centigrade per year of solar cycle length. The average length of a solar cycle over the last few hundred years is 10.7 years and has ranged from 7 years to 16 years.